I want to thank each of you for the opportunity to be here. Malaysia has been just wonderful, and I really appreciate your kind hospitality and your friendship and just the ability to, the opportunity to get to meet some of you and share some time together. So really appreciate the opportunity to be here. The title of this talk, we're going to change gears a little bit. What Rex was talking about is more on the soft side. This is going to be more of a technical side presentation. We're going to be talking a little bit about possibly for many of you a new technique that applies to any kind of testing. Software testing, outside of software testing. I want to bring this up because many of the speakers that we've had this week already have talked about learning from testing. Testing being more than just checking, but gaining knowledge, learning from the testing. And that's what I'm going to talk about. Now the title line that is easy to apply. It is void of mathematical detail, typically, and it's something that is easy to apply. It's a guideline, basically. The other thing I want to talk about is this test design and analysis. I know that test analysis and design, sometimes the word analysis is used before the word design. In my case, analysis for this purpose, for the purpose of this presentation, means analyzing the data that results from testing. So when we test, we create data. We should have some measurements, whether it's counting the number of defects, whatever it is, we should have some measurements. And when we take those measurements and we analyze them, that's what we're talking about. Some people call this evaluation, test and then evaluation. I'm going to call it test design and analysis today. So that's a little bit about the topic. I would like us in the next 40 minutes or so, 35 minutes, to be able to answer the following 3 questions. And I'm going to help you do this. First of all, I'm going to introduce a new term called orthogonality. Now that's a fancy mathematical term. Don't worry about it because we're going to put some simplicity to it. As the moderator said, we're going to keep this simple. Okay? I'm not a very smart guy, so I got to keep it simple. And in order to understand this. So don't worry about the fancy term, although I owe it to you to provide you the actual term that is used in the mathematical arena. And the biggest thing is, why is it important? You'll learn what it is. The question is, why is it important? And why should management, why should leadership know about this concept of orthogonality? All right? That's the first question we're going to answer. The next one is going to be, what are some key considerations that we need to look at when developing a test design? Design and the analysis of the data that comes from the testing are linked at the hip. How you design the test is going to determine how easy or how hard it's going to be to analyze or evaluate the results. That's a key concept in test design and analysis. And so you're going to learn about that. And then lastly, I want to finish up with these rules of thumb or simple guidelines that can allow us to test more effectively, more efficiently, and keep us safe in the test and evaluation business. So to start off, I'm going to introduce perhaps some new terms to you. So this is maybe a new lexicon, and I'm going to describe a test scenario with a very simple graphical construct called an input process output diagram. Testing is a process. And in the process of testing, we have factors or variables that we are going to be looking at. You can think of this as the things that change from one use case to another. Variables or factors. They are shown on the left-hand side up here. And you can see some of these in this web. This is just a simple web-based application where we call it performance tuning. But you have different factors or variables on the left-hand side that could impact performance. The measures that we're going to look at on the output side are performance measures. In this case, one of them is number of homepage loads per second. And of course, cost is always a measure that is of interest to most people. But we're going to home in on the one there, the performance measure called number of homepage loads per second. So let's talk about terminology a little bit further. In the world of combinatorial tests, or statistically designed experiments, which really is the topic of discussion here, we have outputs, which are the measures of performance. They could be number of defects. They could be, like we said here, number of homepage loads per second. These are also called the dependent variables. Why are they dependent? Because they depend on what some of the inputs or the factors are that impact them. So these things go by different names. As Rex said, sometimes the lexicon, the language changes a little bit. So we want to be broad enough in our interpretation to understand that the output could be called a Y variable, like we learned it in school. We learned in school dependent variables typically took on the letter Y. X's are the inputs. Those are, in testing software, these could be what we call test parameters. Sometimes we call them that. They are the independent variables. Those are the folks that we are going to purposely change in a designed experiment. We're going to purposely change them. And then we have levels. The levels could be like a different number of partitions in an EP or equivalence partitioning. Rex mentioned that. But these are the different choices that a factor could take on during a particular test. All right? A run is an experimental test combination. It's a test case. You're going to see that it will be a row in our test matrix here shortly. A replication is doing a test over again. Now, why would we want to do that? Its collection effects are not easy. Tolstoy once said the combination of effects is beyond the comprehension of man. The combination of effects is beyond the comprehension of man. Well, I'm here to tell you, we have test techniques that allow us to get at those interaction effects, and it's not beyond the comprehension of man. So that's what we're going to show you here. Let me give you an example going back to the web-based example. The factors are the inputs here, like CPU type, CPU speed, RAM amount, operating system, virtual memory. Those would be the names of the factors. The choices, or the levels there. Like for CPU type, it could be a Xeon, it could be an Itanium. For operating systems, it could be a Windows or a Linux system. It could be something like that. And here are our performance outputs. So I just listed 2 choices or 2 levels for each of 6 factors. Now, if you were to test all possible combinations, how many tests would we have? We have 2 choices for CPU type, 2 for each of the other 5. How many test cases would we have if we tested all possible combinations? It would be 2 times 2 times 2, 6 times, or 2 to the 6th power, which would be 64. And let's just say these tests are expensive. These aren't that expensive, but if they are, 64 test cases could be quite a bit of time consumed in doing that. The question I want to ask you is, which factors are really the important ones there? Is it CPU type? Is it virtual memory? Is it operating system? Which ones aren't important? How do you know? How are you going to answer that question when you're done with the testing? Furthermore, which combination of those factor choices is going to give us the best result, best possible result? Which will maximize performance? Which combination of factor levels is going to create problems for us? Okay? How do you know for sure? Show me the data. Get used to looking at data. Get used to looking at measurements and analyzing them. So these are the questions we want to answer. So let's go over a couple of traditional approaches so we can compare and contrast what I want to show you today with things that we've learned in the past. One factor to time testing is a very common approach. Medical doctors use this a lot because they will change only one thing. You're on a prescribed protocol of medication, you go in to see the doc, and the doc says, well, we're going to bump that guy up, or we're going to do a test. They probably do only one thing to see what impact that has on the outcome or the performance. They'll change one thing at a time. It's a very easy concept, but there's some very bad news from a software tester's point of view in that situation. Because you'll never be able to get an interaction effects when you test one factor at a time. You'll never be able to build prediction models to assess risk, okay, if you do one factor at a time testing. Now, it's something I learned in school very early. My chemistry teacher told me that if you want to know or understand the impact of temperature on this chemical reaction, you need to hold everything constant and just change temperature. Have you ever heard that before? That's the way I was taught the first time. Now, granted, it's kind of hard to talk about the thing I'm talking to you about, design experiments, to a 15-year-old. But the bottom line is, we're inundated with some of these testing concepts very early in life, some of which are not telling us the complete story. We have to be aware of that. So, Oracle. Oracle is the best guess approach. We use that a lot in testing, where we get our subject matter experts or our domain experts together, and we come up with a set of test cases that we're going to run. Okay? That's the Oracle approach. Then, the approach that is a good approach, if you can afford it, and that's all possible combinations. And that means taking every possible combination of all the factors and their levels and testing them all. Well, that becomes prohibitive when the number of factors gets large and the number of levels gets large, as you well know. The more modern approach, which I present to you this today in all sincerity, that can be used in any kind of test scenario. I don't care if it's unit testing, regression testing, I don't care if it's interoperability testing, functionality testing. This approach can be used anywhere, all right? It's called statistically designed experiments, which I'm going to, simplify that term to DOE, design of experiments. These are the factorial designs, full factorials, or all possible combinations, plus other selected designs that have been generated over time and are available for our use today. So let's look at the Oracle or the best guess approach and give you an example to show you what might not be so good about a test design like that. So let's select, let's not look at all 6 factors, but let's look at 5 of those factors in the web-based application. And I'm going to use coded values to show you the test design. Let's suppose we had 8 subject matter experts in a room, and John, who's going to speak to you next, is definitely an expert, and he says, Mark, I think the best combination of those 5 factors is shown in row 1 or run number 1 there. That is A, which is CPU type, would be the Itanium. B would be the CPU speed of 1 gigahertz, of 2.5 gigahertz, that's coded value 2. C would be a 2 gigabyte RAM, D is 1, so that's a 50 gigabyte hard drive, and E is, I guess, a JTEE virtual memory. Okay? So we test that, and we get a 5. Y, remember, is number of homepage loads per second. Bigger is better for the Y value, and depending on what you're testing, if number of defects is your output, that's not better. Okay? So, but bigger in this case is better. So we have 7 other experts, and they come in and they have their preferred combination that they would like to test. So we test them all, and those are the results. 8 tests, 8 results. Now the question I'm going to ask you is shown at the bottom of this page, and it says, does factor D, that's this factor right here, happens to be hard drive size, but it doesn't matter what it is, does factor D impact the value of Y? Or the average of Y. What do you think? Factor D. Take a look at the column labeled D, and take a look at the column labeled Y. Do you think there's any kind of correlation there? There certainly is. When D is a 1, we're getting 5, 6, 5, and 6, the average of which is 5.5. When D is 2, we're getting 7, 8, 10, and 11, the average of which is 9, almost double the average of which when D is 1. But if you were to say that D impacts Y, you'd have to reconsider that statement. Why? Because look at C. Factor C looks a lot like factor D, doesn't it? In designed experiments terminology, we say C and D are aliased. They are two different names for the same thing. And the same thing is 1, 1, 1, 1, 2, 2, 2, 2. You look at the pattern in the columns labeled C and D, they are identical. And that means you cannot tell what's happening over here to Y but just by looking at D alone. All right? This is a problematic design. Want to know why? Because you can't tell what's impacting Y. Is it D? Is it C? Or is it potentially E? Now, E is not aliased or perfectly confounded with D or C, but it's partial. It's not fully correlated with C or D, but it is partially correlated. Now, I want to bring to your attention now what we call balance in the design. Take a look at the columns A and B. Though the structure there is pretty nice, and here's why it's nice. First of all, in every column, whether it's A, B, C, D, or E, you have 4 1s and 4 2s. That's called vertical balance in the design. You have the same number of low settings as you have high settings. Balance is what we're looking for. That word orthogonality has to do with balance. But not only vertical balance, but horizontal balance. And now here's what I mean by horizontal balance. I mean that for the 4 1s in column A, if you look at column B, half the time B is a 1 and half the time B is a 2. And if you look at the 4 2s in column A, half the time B is a 1 and half the time B is a 2. That's called horizontal balance. Now when you set up these designs or test cases, are you going to have to worry about that? No. Let me assure you we have software that if you have a certain number of factors to test and you want an orthogonal design, it'll generate it for you. But this is not a good scenario simply because you've got C and D alias. From a Venn diagram point of view, you've got C and D. This amount of variation in Y, we don't know what portion of that circle is C, and we don't know what portion of that circle is D. To make it even worse, E, as shown over here, is partially correlated with C and D, and in the crosshatched area there, we have no idea if C is causing that, D is causing that, or E is causing that. We don't want a scenario like this. We want to avoid testing like this because the analysis is going to be difficult at best. So we want this situation over here so that when we're done testing, we can say D caused that, E caused that, and I guess C is the other one I've got up there. C caused that. We want this scenario. Well, how do we get that with orthogonal designs? They allow us to evaluate the effects of factors, and here's the key word, especially for managers and leaders in an organization. Independent evaluation. Independent evaluation is key. Why is it so important? It gets to root cause and effect relationships, which are hard to do, by the way. Okay, so the set of all possible types of testing or experimentation. We've mentioned one factor at a time. I mentioned very briefly equivalence partitioning, and Rex did too. Best guess, I showed you an example of testing techniques, but it's a good one. And here's why it's good, because of the independent evaluation effects that we have. So let's take what is a design experiment, more formally defined. Well, it's the purposeful and systematic changing of your input factors for the purpose of evaluating how they impact the output. So we can find out what's important. Is it A? Is it B? Is it C? And what's not important. So we develop, or I should say software does this for us, and depending on the number of factors and the number of levels, we'll develop what is called an inner array. That's a Taguchi term. Taguchi is a Japanese engineer, or was a Japanese engineer, who did a lot of these types of designs. He's not the only person who's done this, but he has had a major impact in the orthogonal design arena. So, and then the replications would be what he would call in the outer array. So, a famous quote by George Box, who's a DOE design of experiments guru, he said, all experiments, and you know what? All tests are experiments, so you could replace the word experiments up there with all tests. All tests are designed experiments. Some are poorly designed, and some are well designed. The ones that are well designed are the ones that have the balance in it, both vertical and horizontal balance, the concept that we call orthogonality. Let me just show you that this is not some high-polluting concept that is not a concept that you can understand, okay? It's very understandable. Let's suppose we go back, and here are some of the designs that are out there today. You have the Taguchi designs, which are very good for screening. You have the factorial designs, which are good for modeling, typically. You have response surface designs. We have the more recent combinatorial testing designs, like high-throughput testing or all-pairs testing. We have nearly orthogonal and hybrid designs. There's all sorts of designs out there that are available for our use today, depending on the situation we find ourselves. And let's just take a three-factor, two-level design where we have time, temperature, and pressure, a very common scenario in the test world, and it's a chemical process. I'm just using these because we can relate to those. Everybody in this room should be able to relate to time, temperature, and pressure. Well, a full factorial design involves 2 times 2 times 2, or 2 to the third, or 8 possible test cases. Now let's suppose that you knew nothing about what I just talked to you about, balance. And you're asked to fill in the first column for time with either a 5 or a 10. Would it make sense for the 8 slots that are available in column A for me to put 6 5s in there and 2 10s? Would that make sense? It wouldn't. Why? You're destroying balance, vertical balance. So what I'm going to do is put in 4 5s and 4 10s. And I'll bet money that's what you would do too. Maybe not in the order I have them here, but you're going to want 4 5s and 4 10s in column A. All right? Now, the way I'm showing it here, the 4 5s first and then the 4 10s as you look top to bottom, is the way one of the software packages we use does this. So don't worry about that order, but it's a nice order. As you'll see from computer scientists, computer software engineers that you are, you'll see that the patterns here are very familiar to you. Now, temperature, I think we all agree, could either be a 70 or 90, so we're going to have to put 4 70s in there and 4 90s, right? Would it be shabby of me to put 4 70s in the first 4 slots and 4 90s in the last 4 slots? And the answer is yeah, that would not be very good of me. Why? We have the same bloody thing as we had with the CD confounding. So we're going to split them up. We're going to put 2 70s with the 5 and 2 70s with the 10, 2 90s with the 5, and 2 90s with the 10. And I'll bet money, all of you in this room can see what's coming in column C, which has to be either a 100 or a 200. They're alternating, okay? This is balanced now in the design. Now, when the software does the analysis, the tail end, after the data's been collected and it does the analysis, it does it with coded data. By coded data, I mean it changes your low and high settings if you've got a 2-level design into a -1 and a +1. And this is the easiest way if you were to check a design to see if it was orthogonal. I mean, the software does it automatically, but if you say, I don't trust the software, I want to look to see for myself if this is orthogonal, you take a look at every column, it must add up to 0. That is, the minuses and the pluses got to balance each other out. And here's the other thing. When you get the interaction effects is when you multiply 2 columns together. So A and B in the real line values are 5 and 70. If you multiply those together, you get 350. 5 and 90 is 450. 10 and 70 is 700. Now, this column right here, the AB with the uncoded data, is correlated with column A and column B. Not good, because that means we're not going to be able to evaluate the interaction effect independently from column A and B. But if you use coded data, oops, sorry about that. You use coded data, you will see when you multiply column A times column B, a minus times a minus is a plus. A minus times a minus is a plus. Guess what you see in the coded column AB? Again, the sum of the values is 0. And it has a completely uncorrelated pattern with columns A and B, unlike if you use the uncoded data. To make life simpler, let me just show you the full design for this in the coded fashion. I'm going to dispense with the value of 1 here, okay? I'm just going to call it minus and plus. You get the idea. You guys are binary experts. 0 and 1 you use a lot. And all this is right here is your binary representation of the numbers 0 through 7. We call them 1 through 8 because they're the test cases. Now, when you generate the interaction effects, here's how AB is generated. It's obtained by multiplying column A times column B, row by row. Look at the column labeled AB. It's different than any of the other columns. It's completely uncorrelated with any of the other previous columns. Is that good or bad? That's phenomenally good because it's going to allow us to understand what impact it has on the output. Now take a look at AC. You look, and I don't expect you to do the multiplication here this quickly, but a minus times, I'm looking at column A, looking at column C, and the column labeled AC is just a multiplication of column A times column C. Guess what you have in column AC? 4 minuses, 4 pluses. And column AC is completely different, has a completely different structure than any of the other 4 columns. And it's completely independent or uncorrelated with the other 4 columns. There's another column called BC, the same thing. 4 pluses, 4 minuses, adds up to 0, and it has perfect horizontal balance. Completely uncoupled, or I should say, uncorrelated with the previous 5 columns. Now there's one other column. Who's willing to tell me what it is? It's an interaction effect. ABC, thank you very much. Exactly. And there's the 3-way interaction. So if you have 3 factors, you could possibly have up to a 3-way interaction. This design right here, if you do this test design for 3 factors, each at 2 levels, you have the ability to evaluate 7 effects independently. A, B, C, those are called main effects. AB, AC, BC, those are called 2-way interactions, and you also get 1 3-way interaction free of charge. All right? That's an orthogonal design. Okay? So what does this do for us from an intuitive perspective of experimentation and testing? First of all, a statistically designed experiment, or a DOE, is an optimal data collection strategy. It's that you will get more information per data point collected under this strategy than any other strategy you can imagine. Okay? It interrogates the process, like you do as testers. You're testing a process. You're saying, process, tell me what you're going to do or how you're going to behave under these conditions. You may call them use cases. You may call them whatever you like. But you're asking the process to respond to your query. Okay? You use it to identify important relationships between inputs and outputs. You can identify interaction effects. You can use it to optimize the process and estimate and assess risk.